Okay, so this video is going to be finishing up the day 8 notes. Did want to start at the beginning just to go over the stuff we talked about in class yesterday, and for anybody who wasn't in class. The focus of today's notes is really to take what we've been doing in terms of finding coordinates of points on a circle and extend that using some special right triangle relationships that you probably learned in geometry. So just a refresh review, take a look at a 45, 45, 90 triangle. A couple things we should know about them is the two legs of the triangle are the same length. Call them x. That could be any variable. And the relationship between the legs and the hypotenuse is that the hypotenuse is whatever that leg length is times the square root of 2. And if you don't remember that, or as we get into this, you tend to forget, I just want to quickly show you where that comes from. So let's say I set up a Pythagorean theorem with these three sides. So let's call for a second the hypotenuse just c. So x squared plus x squared is c squared. Add x squared and x squared, you get 2x squared. And then if I take the square root of both sides, the square root of c squared is c, and the square root of 2x squared would be the square root of 2 times x. So that's really where that relationship comes from. And it's just that if the two legs are the same, the hypotenuse will end up being root 2 bigger than the leg length. And then a 30, 60, 90 triangle. So quickly label the angles here. In terms of labeling the sides, usually the side opposite the 30-degree angle is your smallest side. So we call that x. The hypotenuse is twice as big as the small side, so we call that 2x. And then the relationship for the other side, you have to think 30, 60, 90 will have a root 3, and 45, 45, 90 will have a root 2 in there, just to keep those straight. So then the third side would be x root 3, where x is the length of the small side. So just in terms of what's bigger, x is the smallest, x root 3 is the next largest side, and 2x is the hypotenuse, which should always be the longest side. And I'm just saying that because if we kind of label these wrong, then it'll throw off our coordinates when we start putting them on a circle. So for example 1, I want to talk about finding the exact value, the exact coordinates of the point at a 150-degree angle with a radius of 6. So just to label this circle, to remind ourselves, it's a circle with a radius of 6, which means these four coordinates on the circle aren't 1, 0, 0, 1, negative 1, 0, 0, negative 1. It's same setup, it's just the radius is 6, so that length is 6, and that's going to come into play when we start labeling our other side. So the next thing you want to do is draw your 150-degree angle. And the remainder of this example and the examples we're going to talk about today in terms of coordinates is we're always going to be looking at the reference angle, because if you think about it, the reference angle of 150 degrees is 30 degrees, and that forms a triangle between the x-axis and your terminal side of your angle. You always want to draw the triangle perpendicular to the x-axis, because then our reference angle, which in this case is 30 degrees, is inside of your triangle, and it creates a 30, 60, 90 triangle. So in terms of labeling the sides, the side opposite the 30-degree angle, I'm going to call it B in this example. You can call it X. The reason I'm not going to call it X is because I'm thinking of coordinates, and I don't want to confuse myself that would be the X value. It's going to end up being the Y value because it's a vertical distance, so I'm just going to label it another variable. So if that side is B, then the hypotenuse is 2B, and you might be able to kind of go past this and really start using the value of the circle, but I just want to show you kind of where this is going to come from. So if that's 2b, the hypotenuse, then the other side would be b root 3. And the one thing we do have to consider is a 150-degree angle puts us in quadrant 2, which actually means the x value should be negative. So there's the relationship between my three sides, and what I want to do is think about the coordinates of the point. So I'm just going to label the point P, Q, T. It's just a point on the circle, and our goal is to find the coordinates without a calculator. So whenever you see exact value, that's without a calculator. So the point will be negative b root 3 b in terms of its coordinates, and what I want to do is find those exact values by using the fact that I can find b using the radius measure that I was given. So if the radius of the circle is 2b, or sorry, if the radius of the circle is 2b and 6, what I can say is 2b, that length, is equal to 6, which means b is equal to 3. So if I know the value of b, if you take a look at your coordinates, you can put 3 in for b and you'll have your exact coordinates. So that means the coordinates of that point, because it's a 30, 60, 90 triangle, and I use the relationship of the sides, I can say that they're exactly negative 3 root 3, comma 3. And you could check that in your calculator. If you remember what we did before, I could take 3 and multiply it by the cosine of 150, or excuse me, 6 and multiply by the cosine of 150, since that's the radius, and 6 and multiply by the cosine or sine of 150. You'll get the same values. The only difference is we'll have to find them exactly, which means no calculator, and have a way to find those coordinates just by using this idea of the triangle that it forms. So with that in mind, if you take a look at A, B, and C, D, E, and F too, but A, B, and C are slightly different. They're more related to the triangle we just did. So I'm going to do the same thing. I drew 3 circles there. I'm going to end up using all of them for those 3 angles. So I'm going to draw a 210 degree angle, puts me down in quadrant 3, and the reference angle is 30 degrees in this case. So what you should be thinking is, this triangle is going to be exactly the same as the triangle we just did. So I'm going to draw the triangle we just did in orange. The only difference is this triangle is going to be below the x-axis. So what I did is went straight to the radius being 6, which in this case is the hypotenuse. And if the vertical distance last time was 3, for the example we just did, then the vertical distance, or the y value of this point, should be negative 3. Same height, just in the negative direction. So if that's negative 3, what you should also notice about those two triangles is they are the same distance away from the origin in terms of their x value. So if you look, the triangles are going to be in the same place in terms of their x value, and their y values will be the opposite, because 210 puts me 30 degrees below the x-axis, whereas 150 degrees puts me 30 degrees above the x-axis. So if I think about what the coordinates might be, the x value should be the same as last time, and the y value should be the opposite of the last triangle. So the exact coordinates of the point are negative 3 root 3, negative 3. So then for B, think about where 330 degrees puts me. Puts me 30 degrees below the x-axis in the 4th quadrant. So there's a 30 degree angle. So if I think about what the coordinates would be, it's the same triangle as before, 30, 60, 90. Still has a hypotenuse of 6. I just got to locate the coordinates of that point where the terminal side hits the circle, and I'm just going to use what we did in the previous 2 examples in terms of what the side lengths would be. So the y value, or the side opposite the 30 degree angle, would be a length of 3, but the coordinate should be negative 3 because I'm below the x-axis. And then the x value would be 3 root 3 because it's the same length but in the positive direction from the origin. So the coordinates of that point would be 3 root 3, comma, negative 3. Same triangle, just in a different quadrant, which means the signs of the coordinates would be slightly different as the previous 2 examples. And then if you look at a 30 degree angle put me in quadrant 1. 30 degrees is the reference angle. So think about that. Then the x value should be the same as the x value in quadrant, or in letter B, except in quadrant 1 and quadrant 4 share the same x value. And then the y value should be positive 3. So if you think about what the coordinates of that point would be, it would be 3 root 3, comma 3. Both coordinates should be positive because we're in quadrant 1. So A, B, and C, and the example before, are all consequences of a 30, 60, 90 triangle, and they're all stem from the fact that the radius was 6. This is obviously not the unit circle. The unit circle is when the radius is 1, but the process will be the same as we get a little bit further into it. So for D, E, and F, these angles are ones that actually end up on a axis, either the x-axis or the y-axis. So if you think about 0 degrees, where would that put me? That would put me right there at that point. So I'm really not marking out any angle. So the coordinates of the point at 0 degrees on this circle would be 6, 0. So we're not being asked for a specific cosine value or a specific sine value. We're just asked for the coordinates, and this is at the point 6, 0. And then pi, remember that's a measure in radians, which would put me halfway around the circle. That's a measure of pi radians. So the coordinates of the point where the angle pi radians hits the circle would be -6, 0. Still on the x-axis, just in the negative direction from 0 degrees or 0 radians. And then the last one, 3 pi over 2, we have to, as we get more comfortable, locate that in radians. We're going to try and not convert to degrees anymore, especially as we get past day 8. But 3 pi over 2 would put me right there on the circle. So the coordinates would be on where the y-axis touches the circle, which would be at 0, -6. So the first 3 examples were a specific angle that puts me somewhere in between the axes, and then D, E, and F put me exactly on an axis, either the x-axis or the y-axis, so we've got to be able to find those coordinates. Now, there's some angles you definitely have to know their radian equivalents. So 30 degrees is pi over 6, 45 degrees is pi over 4, and 60 degrees is pi over 3. That's something we definitely have to know, and I'm going to quickly show you why it is that those angles are true. Now, you can convert them every time, but the goal would be to not have to do that anymore as we get further into this chapter. So if you remember that pi is equal to 180 degrees, if I divided both sides by 6, the left side would become pi over 6, and the right side would become 30 degrees. And that's just showing that they're equivalent. And we showed that pi is equal to 180 degrees the other day, so I just want to quickly show you where that comes from. Instead of going through the process of converting pi over 6 to a degree measure, which you would get 30 degrees, I'm just going to quickly show you the consequence from pi being equal to 180. So there would be 30 degree angle. I'm just going to think about breaking up the top half of the circle in 6 equal increments. So if I do that, take a look there, that's 1, that's pi over 6, that's 2 pi over 6, if I'm just rotating myself around the circle by 30 degrees, or pi over 6, so that'd be 2 pi over 6, which is pi over 3, that'd be another 6th right there at the top, would be 3 pi over 6, which reduces to pi over 2, and you can see that all of those increments are the same, so if I break up pi radians into 6 equal increments, each one would be pi over 6, or each one would be 30 degrees. And then in terms of pi over 6 equal to 30, if I multiply both sides of that by 2, it's just a quick way to show that the left side would become pi over 3, and the right side would become 60 degrees. So the idea is 2 pi over 6's takes me to pi over 3 on the circle, which is also 60 degrees. And then why is pi over 4 equal to 45? If I take pi equal to 180 and divide both sides by 4, I would get pi over 4 equals, and then 180 degrees divided by 4 is 45 degrees. And then where does that put me on the unit circle? Well, that would put me halfway between 0 and pi over 2. So I could also break up 0 to pi in 4 equal increments. So one would be pi over 4. The other one would be 3 pi over 2, or 2 pi, or sorry, the other one would be pi over 2, which would be 2 pi over 4s. And then 3 pi over 4 is that red line there in quadrant 2. And then 4 pi over 4 would put me at pi. So we'll get more into how to break that up, but those 3 angles we definitely have to know. Now, in terms of finding exact values without a calculator, the one thing you'll notice is this example is not tied to a specific circle in terms of its radius. And the reason why is the cosine of 4 pi over 3 will be the same value regardless of what I'm looking at. So let me show you real quick. So if I think about where is 4 pi over 3 on the circle, that's the major part here that is going to be new and important, is I can take 4 pi over 3 and convert it into degrees and find its location. That's fine, but it takes a long time and it's not the way we're going to approach it. So if you think about this, 4 pi over 3 is really pi plus another third. And what that means is, if I'm on my circle, if I rotate from 0 to pi, I need to go another third of pi into quadrant 3. So what that would do is basically make that's 4 pi over 3 right there, which makes, if I draw a quick triangle, makes my reference angle pi over 3, right, the distance between that terminal side and the x-axis. I had to rotate past pi over 3, which makes my reference angle down there pi over 3, or 60 degrees. So what I have is a 30, 60, 90 triangle. And then what I'm going to do is kind of set up these side lengths using the same relationship we talked about at the beginning. So the height, the side opposite the 60 degree angle would be x root 3, the short side times root 3. The only thing is I'm going to make it negative because I'm in quadrant 3. Any coordinate in quadrant 3 is negative x value, negative y value. And the x value would be negative x. Go to the left a certain x distance, so negative x, and then the hypotenuse would be 2x. So that's just the relationship of the sides. I don't know what the radius of the circle is, but in this case I'll show you it's not actually going to affect my value of cosine. So if cosine of 4 pi over 3 is really equal to the opposite side, the adjacent side over the hypotenuse, then I can set that up using the side lengths I have. So cosine of 4 pi over 3 will be negative x, which is the side opposite the reference angle, the side adjacent to the reference angle, divided by the hypotenuse, which is 2x. So I have negative x over 2x, that's cosine of 4 pi over 3, and what you should notice is the x's in this situation will actually reduce. So cosine of 4 pi over 3 is negative 1/2, and that's actually not dependent on the circle that we're talking about, because again the radius and the hypotenuse could have been any number, but because there's a relationship between all three sides, the radius in this case would actually reduce. So what I have is cosine of 4 pi over 3 is going to be negative 1/2, and you can verify that by putting that in your calculator, and you would see that it's negative 1/2 as the cosine value. And I could do a similar process for the sine value just by using the side length relationships that we talked about. So another example, if you look at cosine of 7 pi over 4, the first part of that would be really identifying where 7 pi over 4 lies on the circle, or in terms of a rotation around. So what I think of that is, there's a bunch of ways you can break it up, but I think of that as 2 pi, which would be 8 pi over 4 minus pi over 4. So what that tells me is it's going to be almost a full rotation, but I'm going to really back up pi over 4. So if I think about where that would put me in quadrant 4. So I'll draw that. It's going to put me halfway between 3 pi over 2 and 2 pi, which is 7 pi over 4, which means my reference angle, the distance from the terminal side to the x-axis, would be pi over 4, or 45 degrees. So the type of triangle I have here is a 45, 45, 90, which tells me that the two legs should be the same distance. So I'm going to label the leg across the x-axis as x, and then the other leg will be a length of x, but in the negative direction. So I'm going to call it negative x, which means the hypotenuse is going to be x root 2. So I have my three sides of my triangle in terms of x. So if I set up the cosine of 7 pi over 4 should be the adjacent side to that angle, adjacent side to 45 degrees, divided by the hypotenuse, which in this case would be x divided by x root 2. So I set that up. Cosine of 7 pi over 4 would be the adjacent side, which is x, divided by the hypotenuse, which is x root 2. So how do we find the value of this? Well, the x's in this case would actually reduce, and what I'd have is 1 over the square root of 2. And if I have a radical in the denominator, I want to quickly rationalize that to find the value of cosine in a form that we recognize a little bit more. So to do that, I would multiply the top and bottom by the square root of 2. And what that would give me is the numerator would become 1 times the square root of 2 is the square root of 2. And the denominator would become 2, because root 2 times root 2 is root 4, which is 2. So the cosine of 7 pi over 4 is root 2 over 2. So this is a way to find those exact values on a circle using right triangles. So 45, 45, 90, or a 30, 60, 90. So the other thing we definitely have to talk about is arc length. So we talked about arc length when we have an angle in degrees. So the formula is theta over 360 times 2 pi r. And that's when I have an angle in degrees and I want to find the length that the arc, the angle covers. So if I think about that, so theta is some angle, some central angle. And if I want to find the length of the arc on the circle, I would use, and the angles in degrees, I would use that formula. There's also one for radians. It's actually a lot simpler to do. So the formula for the arc length when the angle is in radians is the radius times the angle. And that's it. And one of the reasons why is because the angle is already a portion of the full circle. So a portion of 2 pi, which is a full rotation. So you don't need the theta over 360 there. But a quick way to kind of remember that is if when we defined radians, we said it's the arc length divided by the radius. So then if I want to find the arc length, I just solve for s. So if I multiply both sides by r, what I get is r times theta is s. And that's exactly what we're dealing with. So if I think about a quick example here is if I had a 45 degree angle or pi over 4 as an angle in radians, how do I find the length of that arc? Well, I would need to know the radius. So let's say in this case the radius is 10 inches. And if I want to find the arc length, I quickly, in my my angle is in radians, not degrees, then I can just take the radius and multiply by the angle. So 10 times pi over 4, when the angle is in radians, would give me 10 pi over 4, or 5 pi over 2. And that's the length of that arc. And one thing we have to think about is if it's a length, the unit would be the same unit as the length of the radius, because we're finding a length, not an angle. Although 5 pi over 2 kind of looks like an angle, it's actually 5 pi over 2 inches. So if we want to make sure we attach a unit when we're given a unit, in this case the unit was inches for the radius, so it'd be inches for the arc length. You can use either formula. It just really depends on what you're given. So we take a look at this example here, example 3. If we want to find the length of an arc, it's a good idea to kind of identify the information that we're given. So we want to find the angle, and we're given the length of the arc, and we're given the radius. So if you think about that, since we have the radius and the arc length, but we don't have the angle, we could actually use either formula in this case. In my opinion, it would be a lot easier to use the arc length for radians, but it doesn't actually matter because we're going to end up solving for the angle anyway. So what I'm going to quickly show you is both methods, so both formulas, and what we'll get is an angle in degrees or an angle in radians, and they should be exactly the same. So let's do that quickly. So the first thing we should do is probably set up one of them, and you got to make a decision on which one you want to do. So let's say we start with the radian one. So there, I'm just going to write both formulas there, just as a review. So let's say we start with the radian one. What do we know? So we know the length is 2 pi, and we know the radius is 18. So then if I set it up, 2 pi equals 18, which is the radius, times the angle, which we don't know. So solve for theta, or get the angle by itself. So I'd divide both sides by 18. And what I'd get is 2 pi over 18 equals the angle in radians, which reduces to pi over 9, and that's the angle. So that would be it. So when you're asked for the angle and you have the radius and the arc, that one will probably be the most straightforward one. But if you're more comfortable with the degrees for now, you can do that as well. So if I want to set this up with degrees, I know that arc length is 2 pi. I don't know the angle, so that's something over 360. And it's 2 pi times the radius, which is 18. So that'd be the setup. Basically put every piece of information we know in there, and we're going to solve for theta, which is what we don't know. So in this case, the answer will be an angle in degrees. So 2 pi equals theta over 360 times 36 pi, if I just multiply that on the inside. Quickest way to simplify this would be reduce 36 and 360. So what I get is 2 pi equals theta over 10 times pi, because 36 over 360 is 1 over 10. So to solve for this, I'd divide both sides by pi first. So I'd get 2 equals theta over 10. And remember, theta is an angle in degrees in this case. So if I multiply both sides by 10, I would get an angle of 20 degrees. So you could check that 20 degrees is exactly equal to pi over 9 radians. So it won't matter which way you do that. You just have to pick based on what information you're given. So that's when you're finding the angle given the arc. Now, if I just want to quickly do a straightforward example where we're given the angle, we're given the radius, and we need to find the arc, it would probably be beneficial to use, in this case, the radian formula, because if you look at the angle in the circle, it's given to us in radians. 3 pi over 4 is the angle in radians. So if I want to set this up, it'd be 3 pi over 4 times the radius, which is 8. So the arc is going to be those two things multiplied together. So 8 times 3 pi over 4, I would reduce the 8 and the 4, which makes that 2. So the arc length is going to be 6 pi. And the unit here, we're not specifically given a radius in inches or meters or feet. So I'm just going to write a generic units. It is a length, which means it shouldn't be like squared units or anything crazy like that. It should just be straightforward. If you don't write units, in this case, it's okay because we weren't explicitly given a unit. So 6 pi units, but that's kind of not that helpful in terms of how long that is. So if you quickly just converted that in your calculator, just so you have an idea, 6 pi would be a totally acceptable answer, especially if you don't have a calculator. But just to give you an idea, that's about 18.85. That's how long the arc AB is, which is the portion of the circle right here, if I color over it. That length is 18.85 or 6 pi units. So that's arc length. That's what we missed. So when you get a chance this weekend, listen to the video, and we will see you on Monday, and hopefully you can accomplish your homework this weekend. Bring any questions you have, and enjoy the rest of your day.